Hello again, this is Charles Sanderson talking about Aspen Custom Modeler and some of its applications. Today I thought I'd talk about data regression and regressing reaction kinetics parameter estimation, it's also called. So from the last model, or from the last session, we had built a little reactor model, and I thought that'd be a good place to start. The first critical step always in doing parameter regression is to make sure your starting model works. So what I have is a simple A goes to B goes to C reaction using a structure, an external structure called reaction, which has got the reaction parameters, the pre-exponential and the pre-exponential and the activation energy. And what I've done is I've offset this to a reference temperature just because that helps the regression fit slightly better. So there's my model. We've run it before, but let's just confirm that it works. So run it in initialization mode, it works. Flip it over into dynamic mode at the flow sheet level. I've plotted the concentrations of data. And so let's run that. And you can see it runs at 10 hours. It's got curves, so the model works, the model's able to converge, all that sort of stuff is good. Okay, so what we'll do is we'll go back to the initial condition. And what I've done also is using the custom table up here, I've created a key data table, which has got from the structures my pre-exponential factors and my activation energy, the temperature of the reactor, and then a couple of other bits and pieces just to, for interest's sake within that reactor. Okay, so the first step is to get some data. What I've done here in Excel is I've made up some data. What I've done is this is some made up experimental data. I've just recast that to be able to plot it. One of the things that I was trying to indicate here is that one of the interesting things with parameter regression is, do you trust the initial point? Do you go with what was measured, or often what's happening in an experiment is people are very carefully weighing out masses of things, and so you maybe know the initial condition to a better degree of accuracy than you would otherwise. So this was just doing a quick comparison of if I fit the data freely or I fit the data forcing the initial condition to be 0.5 in this case. And so you can see I get slightly different results for my regression parameters. For the fun of it, I then did an Arrhenius plot, so 1 over temperature versus log of the rate constant from these different things. And you can see, depending which model I use, whether I fix the 0.5 as the starting concentration or I let that starting concentration float, I end up with slightly different fits. In this graph, they don't look all that different, but what's happening with the traditional formulation of the Arrhenius kinetics, you extrapolate that back to an infinite temperature, or 1 over T is 0. And what you can see is you have a fairly significant difference, although they look fairly similar on the close-up case. So what I tend to do when I'm doing Arrhenius kinetics is I recenter the data. So instead of using T, I use 1 on T minus 1 on T reference, which then recenters the data around 0. And what that does, you get exactly the same mathematical answer, but it breaks some of the covariance or the correlation between the two terms, the reaction rate at a given temperature and the intersection point, or sorry, the slope. So a little bit more detail than you necessarily wanted, but that's what you get when you listen to this nonsense. Okay, so I'm going to come in and do an estimation run. The first thing to do is to come into the tools and open up the estimation tool. What that shows you is then you've got a number of different tabs to fill in. First question is, what am I going to regress? What estimated variables am I going to have? So these are variables that are fixed in a normal dynamic model, but which you're going to try moving around in order to reduce the error or the sum squared errors between a data set and the model predictions. So in this case, I want to use my my pre-exponential factor and my activation energy. So I've got those 4 variables. I simply drag them across. You can see I've got my upper and lower bounds. I can go in and change those bounds. That's usually a pretty good idea because that's going to help get the model to converge more efficiently. So the activation energy has to be positive with the way I formulated the model. The pre-exponential factor can't really be more than 1. So we'll trim those in, and 1e5 is way higher than the activation energy can be, so I'll pin those in as well. You don't have to do that, but the more you can constrain the problem, the easier it is to solve. The other thing to note is when you're doing parameter estimation, or indeed any optimization, ACM is going to move the variables around within the space that you've defined as feasible. And if your model becomes infeasible with certain values, ACM's not going to know that, so it's going to try and go there and may well crash. So setting that lower bound to 0 makes sense. Okay, having done that, I've got to decide what type of experiment have I got. In this case, I'm looking at a batch reactor, so I don't have any steady state experiments, I only have dynamic experiments. So let's create a new dynamic experiment. I'm going to call this T at 50C. I'm going to give it an experimental weighting of 1, and then I don't have anything to copy from, so I'm going to have to set this one up from Go. Okay, so that then creates an instance of an experiment called T50C. And what I'm going to do is I'm going to come over to my data set, and I'm going to grab, first off, I'm going to say what have I got measurements of? And I'm going to say I've got measurements of A and B. So there we go. I've slapped in A and B, and then I can come over to my experimental data, and I can grab data for A and B as a function of time. Close that. So I highlight, I paste, and it's going to say, is column 1 time, is column 2 A? Yes, it is. I can ignore these for now. It's just saying, do I want to skip any of the data? Do I have a maximum number of rows? All that sort of good stuff. Okay, so I've pasted it in. I've now got some experimental data saying this is the data that I'd like to regress against. Can you fit to this, please? What fixed values have I got? In this case, the only one I've got. What's going to differentiate my different experiments? In this case, I've just run the experiments at different temperatures. So the only thing that's differentiating the experiments is the temperature. I can put in time profiles, but in this case, I'm just holding it as a constant temperature. So that's good. And then if I were running the experiments with different starting concentrations or something like that, I might have different initial conditions, and I could drag those and drop them into here. Nonetheless, that's what I've done for now. I've got my experiment put in to the extent that I would like it put in. So I'm going to click done. So now you can see I've got one experiment. If I create another one, maybe T at 60C, now I have the option of copying the T50C example. And so you can see it automatically populates with all the data from the T50C and the same structure. So now it becomes slightly easier. What I can do is copy the data. It's in the same format. Just to be sure, I'm going to replace all existing values. That doesn't really matter unless there's blanks in your data, and then it can go badly wrong. So I always try and check that. And then the starting temperature in this case is 60C, not 50C. So I set that to 60 and I'm good. Okay, so there's the experiment at 60C. I could go in and put the data in for 70C. One thing I would point out is you can come in and click this Create Script button. And what that does is it sort of writes a bit of Visual Basic that essentially recreates everything that I've done manually here. So what I'm going to do, just because I'm being lazy and you don't necessarily want to watch me forever, is I'm going to pull in the data. So here's one I prepared earlier. Here's the script that I ran earlier. Here's the data. So I've now, you see, also got a 70C experiment. The same estimates, except I've lost my initial conditions. So let me just quickly bang those back in again. 1E5, I think I said 1E5, and then 1 and 1. Okay. So that's all good. So I've got my initial conditions and I'm in. If I look at the script that was generated, you can see what it's doing is it's coming in, it's setting the mode to estimation, it's creating a new experiment, it's giving it a weight of 1, giving it a fixed variable, temperature at time 0 is 50, and then it's adding the data points for A and B, where you've got time, value, weighting for each of those. So it does that for the 50C, 60C, 70C experiment. If you come down a little ways, it then says I'm going to add all 3 of these experiments into my system. So this is, often in Visual Basic you have to create a structure and then implement the structure. So that's what's happening here. And then it's coming in and saying, okay, I also want to estimate these 4 variables, so that's that estimated tab. And then finally, there's some other bits and pieces down here that I generally don't worry about. What'll happen in the full script is it'll then actually have a couple of additional commands on the bottom that say, and now run the model. I like not to have that set up because I like to be able to manipulate these things. Okay, so I've got my data in, I can regress the data. One of the reasons I like this reformulation into the reference temperature state is that it lets me actually break the model up into 2 pieces. I can set tref equal to a temperature, say 60C in this data set, and then I can regress just the kref without worrying about the activation energy. So that helps me break the problem into smaller pieces, and often with any optimization problem, if you can solve a series of small bits and then solve the whole thing together, it becomes easier. So what I did to facilitate that is, having created this script, I copied it, I pasted it, I gave it a new name, and I created the key data at 60C only. And I remember now I've made a mistake, so I'm actually going to make that just load experiment 1. So this is exactly the same. I've just deleted a few bits and pieces. So I load up all the data like I did before. I then just load experiment 1, the data at 50C, and then I fit just the 2 krefs, not the activation energy, because the reference temperature is equal to 50C experiment number 1, then I'm off and running to the races. So I'm going to invoke that script. And what you'll see is up here on the estimation tab, tools, estimation, now I'm only fitting those 2 data points, and in the dynamic experiment I've only got the 1 data point, or the 1 experiment to fit. Okay, so I'm off and I'm finally ready to run my model. I go to estimation, I hit run, and you can see what it's done is it started off with an experimental error, or a sum of squared errors of 0.1. It's reduced that down to 0.4. It's got a fairly good fit to the data. It's fitting the kref for decay and the kref for production. It's got values of those of about 0.2, 0.02, and 0.2. The standard error on those fits is pretty small, so the confidence interval doesn't cross 0. So what this is telling me, because this standard error is small relative to the value, particularly for the production rate constant, it's telling me that these are probably pretty good estimates. I can come in and do some other statistics. It's always interesting to look at the correlation factor. At least I find it interesting. You can see whether the things that you're fitting correlate strongly to each other. In this case, 0.5, they're not strongly correlated. So that's good. Those 2 reactions are independent and they're not messing with each other. It then talks about how well it fits the overall data, and then it gives you the details on individual experiments. So you've got this is what was measured, this is what the model predicts, so this is the percentage error, this is the residual error, and so on. So you can really drill down and see where the errors are and where the gaps are if you want to. If you want to do it graphically, you can come in, estimation, and then unfortunately this is a bit clunky. You've got to come into individual experiments and individual rows of the experiment, but then you can start seeing, you can plot, and then the dots of the data, blue is the model fit. You can see it's not doing too badly. It's hitting most of those data points and coming up with some fairly good stuff. Okay, so that was me fitting just the kref. Now let's go back and fit everything all at once now that I've got decent estimates for that kref. I'm going to clear out that so I'm off and running. You saw I double-clicked to run the script. What that script now has done is it's now got all 4 variables and all 3 experiments. So let's run that. And you can see once again it starts off with a moderate error. It doesn't always improve the error. It actually gets slightly worse before it gets better. Now I've come in, I've got estimates. Interestingly, my estimate for the decay, the activation energy on the decay reaction, the standard error is bigger than the estimated value, so that's really not a very good estimate. The others are looking pretty decent. That activation's a little higher than I'd like it to be, but that's not catastrophic. If I come in and look at the correlation matrix, you can see, unsurprisingly, the K and the EA for reaction 1, so 1, 3, has a fairly high correlation coefficient, and similarly 2, 4 has a fairly high correlation coefficient. If I hadn't done the model reformulation, if kref was at infinite temperature, then I guarantee those correlation values would be much higher. Okay, so I've got a halfway decent fit to the data. What could I do to improve it? Well, perhaps I've got values of C that were measured as well, maybe off the same analytical instrument. Technically, I don't need them. I just need to fit A and B to get the data. But if I have the data for C as well, that's kind of like a cross-reference on my mass balance. Extra redundant data is hopefully going to help me fit the data better. So what I've done is I then pull what I've written another script where what I've done now is add to those experiments the concentrations for C. Okay, so let's have a look and see what that does. What I'm going to do is I'm going to grab this chunk here and just put that into a text editor for now. So this is A, B only. So I'm going to then clear all this data out. I've got my new experimental data, set it off and running. Once again, it's come through, it's come up with some new estimates. And if I compare those, so now this is A, B, C. You can see it's still not a great fit, but I've gone from 1.4 times 10 to the 3 to 0.7 times 10 to the 3. So I've halved my standard error, improving the overall fit. Some of the other estimates have tightened up as well. You can see all those other ones have got a lower standard error. The values have moved slightly as well. So having more data definitely helps. The other thing that's always interesting, you remember back in Excel, I was saying there's a difference between do you use the initial point or do you use the hard experimental data for the initial point. If what we do is we come in and we use the hard initial data for the initial point, now in my estimation, the concentration of A is starting at 0.5. If I rerun my fitting, again, it's come up with some values. Is that a better fit? Well, it's maybe brought that standard error down slightly across the board, in fact. So that seems to have helped things as well. So knowing what that starting point is helps me tidy things up slightly more. What else can I? My confidence interval, though, is still crossing the 0 bound, which is not great. So the final thing I've done is I've gone through and gone back to the lab and say, hey, can you run me some more experimental data? I'm not getting a good enough fit yet. So I have even more experimental data. And so now what I've done is I've had them run another experiment at 40C which has got the same sort of data structure as everything else. I've got A, B, and C. I've now got 4 experiments, not just 3. One other point I was going to make before I run is it's running really fast because it's a small and simple model. As you get into more and more complex models, it'll run slower and slower. And so what you want to do is minimize the amount of work that ACM is doing in the background. So having this plot open is a really bad idea. I would delete that plot. The other thing the other thing that I tend to do when I'm doing large, I'm sorry, I'm not being very clear. The other thing I do when I'm doing large models is have a look at the communication interval. I don't actually need it to be very high. The communication interval, what happens in ACM, you've got sort of two bits of software. You've got the numerical system underneath that's doing the integration, and that handshakes with the GUI software that sort of tells the user what's happening with the model. So if you've got plots like I just deleted, the data points on that plot will update every communication interval. So in this case, I was getting the data every 1 hour. That requires handshaking and data to be passed back and forth. With large complex models, that can actually be a significant CPU load. So what I try and do is make the communication interval around about the same as the experimental time for the data. And what that does is it just reduces the number of handshakes down to essentially 2, the start point and the end point. And then the internal numerics is doing all the good stuff in the background, but you're not getting the GUI spending a bunch of time flickering and updating. So that's another smart move to try and make. Okay, final run. Here we go. With all the data, all 4 experiments, I've run through. You can see this is all growing. And you can see now at long last my standard error is smaller anyway, relative to my actual value. My confidence bound isn't crossing 0. So I've got a halfway decent fit to the model. Is it great? No, it probably could still use some more work, but hopefully now you've got a flavor of how to do parameter regression estimation in optimization in ACM. Give me a call, drop me a comment, let me know what you think, and I would be happy to try and help. Thank you. Goodbye.